Welcome to your chance to self-assess in a review. We're going to go through 8 weeks, 16 concepts in stormwater management class. These build on a lot of other concepts that you should have at least been exposed to prior, primarily the concept of units and how, in fact, everything is based on slugs, feet, seconds, or pounds, feet, seconds on the imperial side, and kilograms, meters, seconds, or newtons, meters, seconds on the metric side, knowing that 1 kilogram weighs 2.205 pounds and also has a force on it of 9.8 newtons are some of the basics of what you should walk into this class understanding. We will be applying these through 8 weeks, 16 concepts. I will provide some links and you can provide others to each of these concepts. First and foremost, to start, vectors are three-dimensional. They have a magnitude and a direction, which in fact are two directions from a standard position angle in an X and Y plane and a direction actually up or down from that plane. We call those theta and phi, or that can be written in standard engineering notation I, J, K, with I being a unit vector in the X direction, J a unit vector in the Y direction, and K a unit vector in the Z direction. Writing in that notation makes a lot of mathematics a lot easier. You must actively define and notate your coordinate systems and datums. The second step in any standard problem-solving system is to notate and define your coordinate systems. Sometimes coordinate systems will change throughout a problem, and you have to know that two coordinate systems are related to each other by translation first, then rotation, 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 and perhaps a couple of or three scales. Datums are not only X, Y, Z datums, pressure datums, time datums, etc. You have to understand that the unit vector and the direction of the vector has a length of 1. There are lots of different ways to get it, but when you do get the unit vector, you call it lambda, and then the vector itself is defined by the magnitude times that unit vector lambda. Lots of different ways to get it, but lambda will have a length of 1 and it will give the direction of the vector. We looking forward to lots of implications of integral math or differential math. We looked at kinematic equations and decided they are in fact three-dimensional and they are also parametric equations. In other words, X, Y, and Z position are all functions of time. We've looked at, again, the fact that a position is nothing more than a position vector, usually emanating from whatever is defined as your origin is a pointer more or less to where your thing is at. That means as that position vector changes with respect to time, you get velocity, and as that velocity vector changes with respect to time, you get acceleration. We now understood that we understand on the world we understand that the gravitation acceleration due to gravity, normally known as g, is down, and it is 9.8 meters per second squared, or 32.2 feet per second squared. Another great way to do a conversion. Centripetal acceleration is equal to the velocity squared over the radius if something is going around a circle, or the angular velocity squared times the radius. You notice one is division, one is multiplication. You remember we worked out in class that angular velocity is actually the cross product of the radial vector and the velocity vector divided by the magnitude of the radial vector squared. Scalar and vector products of vectors are huge. They have many, many applications, and mathematically they are pretty straightforward to solve because they can be done graphically when you stack up a matrix that can kind of help you out in calculating both the scalar and the vector product. They really each only have one definition. The dot product is the dot product, and the cross product is the cross product. Just like 1 plus 1 is 2. You can, however, solve them graphically. You can use the determinant for the cross product, or you can use a magnitude times a trigonometric function. Cosine being what it is for the dot product, and sine being what it is for the cross product, with the dot product giving us a scalar and the cross product giving us a vector whose direction is defined by the right-hand rule, or in fact out of the plane defined by the two vectors. 16 concepts, 8 weeks. Again, a review from a couple of semesters ago. The change in pressure is equal to a negative of the change in elevation times the unit weight through which you travel. Remember that the unit weight of any fluid that's not water is equal to the specific gravity times the unit weight of water. Remembering that the specific gravity of water is 1. Also remembering that you will very often see this equation as change in pressure equals change in depth times the unit weight through which you travel. It is the same equation. Pressure conversions are sometimes datum shift, sometimes scale shift, and sometimes both. Understanding what one atmosphere values are for the systems helps out a lot. An atmosphere is the same as 14.7 pounds per square inch, which is the same as 760 millimeters of mercury. All the other conversions are generally related to those by understanding the specific gravity of mercury is 13.6, and understand that there are a gross of square inches in a square foot. Looking at hydrostatics, we will see this come back at us many times within structures, but we have to understand that the area under a pressure versus area curve is the value of the resultant, and the resultant is placed at the centroid. We can do that with mass prop, we can do that with any other set of tools that are provided by a software, or we can do it by a weighted average of distance weighted to the area if you have a series of different shapes which you put together. Hydrostatics is your introduction to statics, which more or less is the application of Newton's laws to equilibrium. Sum of the forces equals 0, sum of the moments equals 0. We looked again at free body diagrams, understanding that we have to account for gravity, which is quote-unquote touching, or electromagnetic force, which is quote-unquote touching, but we also have to account for everything that is actually touching it, including fluid interfaces such as water or air, which are distributed, just like weight is distributed over the entirety of something that has mass. We reviewed conservation of energy and came to the fact that, in fact, if you drop a ball a distance h, its velocity will increase the square root of 2gh. That is because potential energy is mgh, and kinetic energy of translation is 1/2 mv squared. It gets a little more complicated as we add potential energy to a spring or kinetic energy due to rotation, but not much more so. Conservation of mass. If there is no storage in the system, the mass flowing in equals the mass flowing out, or the mass flowing through any point in the system is equal. That very often looks like Q1 equals Q2, or velocity times area equals velocity times area. That is because if the unit weight or density is not changing, you can take those factors out of the equation. Bernoulli's equation in words: the elevation energy per pound of material plus the pressure energy per pound of material plus the velocity energy per pound of material plus the head of the pump equals the same plus some head loss. And there you go. Head loss finally is proportional to velocity head. We will mark this up with links, and hopefully you can self-notate if you're going to those links on what you do in fact understand and how much you in fact have studied any or each of these things.